What is the asterisk mean?
That. Is that? That's what.
Oh, okay.
All right. Other questions?
Yeah, please use tomorrow, right?
Yes. Double check this written over here, go. Tomorrow's the 31st, quiz on the 14th.
And so the master set's due on the next following Tuesday.
That is correct.
And so the lab.
Yes, that would be the case as well. I guess I don't generally write what the labs are due, but sometimes they do. So the simple harmonic motion one's due today, and this is the simple pendulum. And when are you having something removed?
April the 5th.
April 5th. Okay, so next Tuesday. All right. Other questions? All right. Quick. So that was 14. Let's get into chapter 21. In a moment.
I have my lab in tomorrow. I'll be
Okay.
finished with it. Just to let you know. Kind of behind, but I'll have it tomorrow.
All right, so this chapter is dealing with mechanical waves. As opposed to electromagnetic waves, parenthetically right over here, which in general electromagnetic will be getting into more detail in a week or so. So mechanical waves are ones that require a medium. So, as in sound is a mechanical wave because it requires air to be able to be transmitted from one person to another. Because as I'm sure we all know, in space, no one can hear you scream. Among mechanical waves, there's two major types. Longitudinal and transverse. Now, which wave it is depends upon how the particles in this medium will react. So I guess mechanical wave requires medium. And I say medium as it requires something to actually vibrate or move. So longitudinal, if you think about when we were dealing with Young's modulus, so we applied a longitudinal force to it, or there was longitudinal strain and the transverse strain was perpendicular to that. Longitudinal wave, the particles that are vibrating move parallel or anti-parallel that's the word anti-parallel to the wave itself. I'll get a better one. So a quick example here is I have a slinky. Wait for it to calm down a little bit. I'm hoping you can see the coils. I'm going to release some of the coils at the top. Did you see something go all the way down to the bottom?
Yes.
That is a wave, but did any of the coils actually go all the way down to the bottom? Or at least any of the coils at the top actually travel all the way that distance?
No.
No.
The coils themselves just moved down a little bit and then they moved back up. But the wave itself moved all the way down. So the particles, the coils, moved with the wave or opposite the direction of the wave. So parallel or anti-parallel to the wave itself. And that's an example of a longitudinal wave. An example, sound is a longitudinal wave. In geology, P waves, and then we're just going to call it a slinky pulse. And I'll go into more detail, a little bit more detail on what a P wave is after we talk about transverse, because transverse is going to have S waves, and it's, I think, convenient to talk about them both at the same time. In a transverse wave, particles, as the name implies, move perpendicular to the wave. So, for example, a stadium wave. In a stadium wave, people are moving up and down. They're the particles, but the wave itself will be traveling one way or the other around the stadium. S waves in geology, or more specifically, seismology. And then I'm going to put down long coil, which is going to be a demonstration we'll do in the hallway in just a moment. So the P waves and S waves, the P stands for one of two things. It either stands for primary or pressure. Because pressure is caused by one particle hitting another, hitting something else. We feel air pressure because air molecules are bouncing against us. Balloon feels pressure because you have air on the inside and outside, both bouncing against each other. So a longitudinal wave in general is caused by one particle smacking into another one, causing it to, the next one to then hit another particle, to hit another particle, hit another particle.
So like dominoes.
Yes. I'll throw that on here, like dominoes. Yes? Sure.
Yeah,
It is, okay.
pretty sure.
So this particle tells two friends, and that particle tells two friends, and so on. So when I'm producing sound out of my throat, I have a vocal cord that's vibrating back and forth, pushing air molecules together and basically compressing them and rarefying them. But the particles that are coming out of my throat are not the ones hitting your ear. At least not at the time you hear it. Eventually, it will eventually get there. or some of it will get there.
Wouldn't them be the waves that bounce back that you are hearing?
Wait, say that again?
The waves going this way, and it takes so many seconds, and then the waves that's bounced back from that wave you're hearing.
Oh, they're talking about echo. Or, I mean, the wave, I produce pressure coming out of my throat, the pressure
Right.
wave, the longitudinal wave, and then those particles that are coming out of my throat are gonna hit other air.
And then it's gonna come back, because you're gonna listen to the vibration.
Well, what you're initially hearing is just basically it's not it coming back, it's that the wave hits, these particles hit these particles, which hit these particles, and eventually, through a chain reaction, some of those particles smack into your ear and hit your eardrum. Are you talking about when you say coming back?
Well, you got air pressure coming from your vocal cords out to your mouth so it's coming out of your mouth, and then it reaches a point that all that air pressure, that the molecules gonna come back and hit your ears.
I'm getting caught up on when you say coming back and hitting your ear.
Cause your ears have to hear something.
Right.
You're gonna hear vibrations.
Right, which is caused by the air molecules smacking into your eardrum.
Okay.
The higher. When you're talking about coming back, all right, so.
You got sound coming through your mouth.
Right.
Okay.
Something that we recognize as sound.
Okay, sound's coming out. And then your interceptors in your ears hear vibration.
Right, I agree with that.
So from your mouth is air particles coming out your mouth.
Right.
And then it's coming back to hit your ears. Something smacking to.
Right, but the particles that are smacking into your ears are not the ones coming out of my mouth.
Okay.
That I have a particle here that gets forced out of my throat.
Right, from pressure.
Right. Different ways of looking at it. Which then hits another particle, which hits another particle, which hits another particle, which hits another particle, and eventually through a whole bunch of particles hitting particles, that reaches the ear. So it's a chain of events that gets it there. I feel like we're out of sync right now.
Because you talking, you hear yourself.
Okay.
That's
because
what I'm
again, it's
saying.
hitting air, it's other particles, and eventually.
Okay, it reciprocate back.
Yeah, I mean, it's not a straight line like this.
Okay.
It,
It goes like this. It spreads out.
right. Yeah, I don't think we're as out of sync as.
Yeah, because your voice is on a certain frequency, 3K to 300K. Frequency, your voice.
Wouldn't sound waves be more like a pebble hitting into the water and rippling out like waves?
Yeah, that's an analogy that I'll use later on. We'll talk about sonic booms. Yeah. Doppler effect.
It's not omnidirectional, it goes everywhere.
Yeah, it goes everywhere. No, no.
Like it
Okay.
goes.
Sorry, I was missing what you're going for. All right, I will move on. The S here stands for either shear or secondary. So, Earth. There's an earthquake over here. That earthquake has the shifting of the Earth I think typically you have two plates that are pressed up against each other and there's a quick slip. So you get this sudden shock to the system and you basically have different types of waves being generated. You have And so if I've got a seismograph over here, drawing more of the old school version, because that's the one I still picture. It's gonna pick up any vibrations that get sent to it. Well, you have these waves that are being sent out as pressure waves. And the pressure waves get there first, thus primary. The shear waves, since they are transverse, this is caused by one particle pulling on another. Whereas this is more pushing, transverse is more pulling. One particle pulls onto. Suddenly doesn't look right. That's worse. All right, so one particle pulls on another. So a huge difference between these two waves in this particular situation is that if I have one particle pulling on another, so a transverse wave is as I pull up on this, these coils are pulling on the coils next to it, and then when this comes down, it pulls the other coils next to it down. So you get this. So that was almost worthless demonstration right there. So a shear wave requires one particle to be bounded with the one next to it enough so that when it moves, it pulls the next one with it. Whereas longitudinal, you just have one just smacking into another. The implication here is that the S waves, the shear or secondary waves, travel best through solids. Whereas longitudinal waves can travel through, well, any of the four major states of matter. Glass, gas, liquid, solid, plasma. And from what I've read on the 14 different states of matter, it actually probably traveled through everything except the Bose-Einstein condensates. So we get these primary waves coming up to here. The secondary waves, because they travel through solids, this was one of those big pieces of evidence to tell us that the center of the Earth is not solid. Because you can go through calculations, because there are formulas out there, we'll get to some of them, formulas about how fast a wave will travel. We can figure out how fast this gets to us. The secondary waves, we can figure out, well, they couldn't have been traveling through the core because it's taking too long. They must be going around the outside of the Earth. You calculate how long that should take, it matches up with what we're seeing, and so this would tell us that there's some sort of crust on the outside here, and then some sort of liquid nougaty miracle in the middle.
Doesn't longitudinal waves travel faster through solids?
Yes. Thus putting your head on a train track to hear if the train's coming. You never know. If you put your ear down on a train track, you should be able to hear the train's coming before you would catch it through the air, because the vibrations are traveling through the rail. An example of it, because we're dealing with the longitudinal waves, again, as one moves, how quickly does the next one react to it? If I've got a solid table here, I push on this end, that end's pretty much moving at the exact same moment. Whereas sound, because it requires a lot of intermediaries of transferring energy from one to the next, to the next, to the next. Well, I guess this does too, but the solid, less compressible. All right, it seemed quiet enough in the hallway. Let's mosey out there. And I will need a volunteer, and I may as well pause this.